Okay, so last lecture we discussed the product of a family of topological spaces. Today I want to do the union, or disjoint union, and also the pushout, which is just the sort of general way of talking about gluing spaces onto one another. Okay. So given a family of topological spaces, let's just say disjoint union for the moment, and I'll explain why this language coproduct exists in a minute. So the disjoint union of the family of topological spaces, well, first of all, it's just a disjoint union set. That doesn't cause any problems for us. That's the set. So there's sort of a standard way of realizing that as a set, right? Which is just to take the set of all pairs where the first element of the pair is an index and the second element of the pair is an element of the corresponding set. That makes sure all the sets are disjoint, viewed as subsets of this. So without further comment, I'll view each xi as a subset of the disjoint union. Right? That's a natural thing to do. Okay, so it's that set with the topology. Now here there's no tricky thing going on like there was with the products. So I just tell you the topology. I don't have to tell you a basis. I just tell you straight up what the open sets are. So the open sets are the disjoint unions of open subsets of the xi. Right, so given a family of open subsets of each xi, I take the disjoint union of the ui's. There's a natural function which just takes, if you want to think about them as pairs, takes a pair that looks like that and just sends it to the same pair viewed as an element of the disjoint union of the xi. So that's a subset. I declare that open, and that's all the open sets. Okay, so exercise. Check this is a topology. It's just sort of routine. It's not really worth our time doing in class. Just observe. You just have to think about if I take an infinite disjoint union and I intersect it with another infinite disjoint union, just write down what that intersection looks like. Use this notation if you find it helpful. And you'll see that it's literally just, so if I take disjoint union 1, intersect disjoint union 2, then I just get the disjoint union of all the intersections, right? Which is clearly, again, of this type. So that's the only real tricky case. Okay, so that's the disjoint union with its natural topology. What's this word coproduct? Well, it's because the disjoint union is dual in a precise sense to the product, and that's why the notation is this upside down product, right? That's the reason for that. Precise sense in which it's dual is sort of categorical thing, and we're not talking about category theory in this class, so I won't really spell out precisely why this notation is reasonable. So I should add to this, check that this is a topology and that the functions which sit each xi, or xj say, inside the disjoint union is continuous. So for the product, we have the projection maps. Those are the things we want to consider for the disjoint union, we have these canonical inclusions. We went through the proof of what I called the universal property of the product last time, which was some formula which told you how to compute all the continuous maps into a product. There's a Joule statement for the disjoint union. I won't prove it, it's an exercise, which says that for any topological space Y, if I wanted to find a continuous map out of the disjoint union, it's the same data to specify a continuous map out of some xi. Okay? Right, the right-hand side is the disjoint union of all those things. So to specify an element over there is just to pick an I and pick a continuous map from xi to y. And that's precisely the same data as giving a continuous map from the disjoint union to y. Oh. Forget that. It's Monday morning. Hey, that was all garbage. Well, I hope you were confused, otherwise you weren't paying attention. Because, I mean, think about a continuous map out of this, right? It has to send everything in here somewhere, right? So it's not defined on just a single xi. It has to be telling you something about all of them. All right. So a continuous map out of this, well, just think about all the xi's as sitting inside the disjoint union. There's the disjoint union. You've specified a map to y. If I restrict that map to each of the xi's, I certainly get a sequence of continuous maps as on the right-hand side. So that tells you how to map the left to the right. And the claim is that, well, it's surjective, so that every family like that of continuous maps from the xi's can be lifted. Well, it's clear what to define on the set function level as a function out of this to this. And then the claim is that's also continuous. And that's where the topology, that's why the topology is defined the way it is. All right. Okay, any questions about the disjoint union? So I think this should seem more straightforward than the product, right? The product. I think one of you was asking a question at the end of last lecture, which I answered incorrectly, so let me correct that now. So if you think about the product, I defined a basis to be products of open sets where all but finitely many were the same as the whole space, right? That gives you the topology that we want. There's another topology, which is when you just take what you may have thought naturally, which is inside the product, well, you take for every I an open subset of xi and take the product over all of them. Okay? That will give you a basis. Right? Someone asked me, and I thought that it didn't actually give a basis. I mean, it is a basis, but it's a basis for a different topology. It's actually different. Right? So it's a genuinely different topology. If you want to see that, think about continuous maps into, say, a countable product of so take this topology on this guy and think about it. Think about the function, which is just the identity in every degree, and you'll see that if you take this other topology, the one I just described, that's not actually continuous, which is certainly not what you want. Right? Okay, so there's sort of two obvious topologies you might put on the product of an infinite family of topological spaces. One of them is wrong. Okay. All right, so let's talk about the quotient. So given a topological space, an equivalence relation on X, what we want to do is we want to make the set of equivalence classes of that equivalence relation into a topological space. Well, why do we want to do that? Well, I'll explain in a moment. That's how you glue spaces together. So this is a very central construction. So how are we going to do that? Well, we know how to form the set of equivalence classes, right? That's x mod tilde. And there's this map which just sends an element to its equivalence class. I mean, that better be continuous, right, for this to be even the most slightly reasonable definition. So we just define the topology so that that's continuous. The quotient space is just the usual set of equivalence classes with the topology let's write it like this. So the topology on x mod tilde is all those subsets, so sets of equivalence classes, such that when I take each equivalence class and just unpack it, the resulting subset of x is open. Okay, so where rho is the quotient map. I mean, all those sets better be open for this to be continuous, and then the claim is actually that is a topology. Right, again, that's an exercise to check. Okay. So what's this space good for? Well, so I've emphasized a few times already in this discussion of topological spaces that maybe what's more important, or even more important than the topology, maybe, is the set of all continuous functions out of a space. Right? So the whole point of forming this quotient is that it has some good property with respect to maps out of it, and this is the property. So given a continuous map from x to y, such that f of x1 equals f of x2 whenever x1 is equivalent to x2, right? So we've got some equivalence relation on x, and suppose f respects the equivalence relation. So it collapses equivalence classes to the same element of y. There is a unique continuous function such that the following diagram commutes. So that's the quotient. This is f. It's little f. All right, so capital F just sends an equivalence class. Well, everything in the equivalence class goes to the same place by hypothesis, so it's clear how to define f at the level as a function. And then the topology guarantees that f is continuous. And the uniqueness is clear because it's the unique function that makes that work. Okay, so notice that the set of all pairs such that fx equals fy, this will come up in a minute. So you all should have thought about, the equivalence relation generated by a set of pairs at some point, right? So if I have a set X, and I take just a set of pairs. They don't need to satisfy the hypotheses to be an equivalence relation. Well, take the set of all equivalence relations which contain that set of pairs, and take the intersection over all of them. That's still an equivalence relation, and it's the smallest equivalence relation which contains the given set of pairs. That's called the equivalence relation generated by a set of pairs. Because it's extremely tedious to say an equivalence relation sort of explicitly. Usually you say, I want the following things, the following list of things to be equivalent, and then take the equivalence relation which is generated by those. Okay, so the point of mentioning that is that suppose I give you a collection of pairs which happen to lie in this set. That is, they happen to go to the same thing under F. Well, this set of pairs here, the set of x, y, such that f of x equals f of y, that's reflexive, symmetric, transitive, right? That is an equivalence relation. So if I have a set of pairs which are sent to the same thing by f, well, the equivalence relation generated by that set of pairs is also contained in here, right? By definition, it's the smallest equivalence relation containing those pairs. So if this set contains those pairs, this contains the equivalence relation. Okay, so that'll come up in a sec. All right, so that's disjoint unions and quotient spaces, and now we want to combine the two to form what's called the pushout. And this may seem a bit abstract at first. So the reason we want the pushout is that it's a way of generating many examples of topological spaces. And the input data is two continuous maps, which I'm calling, what, F and G. So the pushout well, strictly speaking, so we define the product. That was really not just a topological space. It was a topological space together with all those projection maps. That data together is what I mean when I say the product, actually. The disjoint union is really that topological space together with all those inclusions. The quotient space is really that topological space together with the quotient map. That's a sort of package. The pushout is the topological space, which is the disjoint union of y and z, okay, modulo an equivalence relation, where tilde is the equivalence, let's say smallest equivalence relation containing the pairs fx, gx for all x in x. Right, so take the collection of pairs, f of x, g of x, where x ranges over all elements of x. That is well, think about f of x. What's f of x? That's an element of y, right? But I can think about any element of y as an element of the disjoint union. I can take g of x, think about that as an element of the disjoint union, and then I take the pair of elements of the disjoint union, which is f of x comma g of x, interpreted as I just suggested, and then take the equivalence relation, the smallest equivalence relation which contains all those pairs, and then mod out by that equivalence relation, and that's some new topological space. Together with the continuous, well, together with the maps, what do I call them here? Okay, so there's a map from y to the disjoint union and then to the quotient. I'm just going to write that as O to y. and then there's similarly an iota z. I don't need to check those are continuous, right? Because, well, we already discussed that the inclusion into the disjoint union is continuous and the quotient map is continuous, so the composites are continuous. All right, so I've now defined a topological space and two continuous maps. Well, why do we care about this particular combination? All right, so what does the pushout do? The quotient, what it does is that it's the thing that all maps agreeing on equivalence classes factor through. That's what that exercise over there says. So the pushout does the following. Given continuous maps, so one from Y to some space and one from Z to some space, such that the diagram, which is made up by all this data now on the board, so that's F, that's G, that's U, and that's V. So such that that commutes. So remember, that just means that U after F is equal to V after G. There is a unique continuous map. Let's call it T. From this space such that T after iota Y is equal to U and T after iota Z is equal to V, i.e. the following diagram commutes. So there's my X, there's Y, there's Z. Here I'm going to put this was my original diagram. There's F, this is iota Z, and that's iota Y. Observe this diagram commutes, right? If I do by construction, right? Because what does this diagram do? It takes an element X, it sends it to F of X, and then it sits F of X inside the disjoint union as F of X, and then looks at the equivalence class of F of X. This way around the diagram sends X to G of X, and then looks at the equivalence class of G of X. But the whole point of that equivalence relation is that it made those two the same equivalence class. All right? So the whole point of defining that thing was that this diagram commutes, and it's actually the sort of minimal thing of that kind. It's the minimal way to take those two arrows going away from X and make them come back together into a diagram that commutes. It's minimal, precise, I mean in the precise sense that it's a sort of less than or equal to every other thing of that kind, right? If I take something else of that kind, what I'm saying is there's an arrow, T to W, which makes that thing which allows me to obtain that diagram from this one. That is, T after iota Y is equal to U, and T after iota Z is equal to V. Okay, so let me indicate these two equations by just drawing a little circle here to say that those two triangles commute. So, i.e., this diagram commutes. Okay, and T is unique. So this may seem like a bit of an abstract statement. We'll give the proof, And then I'll show you how to use this construction to just sort of basically realize any construction you can sort of think of in your head as gluing together lines and points and spheres and so on. I mean, there's sort of an algorithm you can run in your head that makes sense intuitively about building topological spaces. And this is the way of actually doing that in the most efficient way. Okay, so let's give the proof. So what have we got? We've got F and we've got G. So we're given that commutative diagram, and I have to define T. Well, I don't have any choice about how to define T, right? Because what's T defined on? Well, it's defined on a set of equivalence classes of an equivalence relation on the disjoint union. So so every element in that pushout, y disjoint union subscript x, z, by the way, the subscript there is because you're sort of pushing out away from x, that's the idea. So if I give you a y in y, well, I can think about y as an element of the disjoint union, and then I can take its equivalence class. But that is, by definition, T of iota y of y, right? So if my T were to satisfy the conditions, that is, T of iota y would have to be u, I'd have to have that be u of y. And similarly, I'd need this to be v of z. Okay, so I had no choice about how to define T. That's the uniqueness part. But we need to check that's continuous, right? And well-defined. And the fact that's well-defined is actually relies on commutativity of that diagram, if you think about it. Right? Okay, so the easy way to induce the T is instead to use what we already know about the things that went into it. So this is what we need to get to, but rather than check continuity directly from this definition, and we'd also have to check this is well defined, well, let's go back to, first of all, the disjoint union, right? So if I take U and V, that's a map out of two spaces to W. Did I erase it, did I? I see, okay. But we know, right, by definition of the disjoint union, that continuous maps out of a disjoint union of a pair is the same as a pair of continuous maps. What that's saying in practice is just that if you take a continuous map from y to w and z to w and you write down the natural function from the disjoint union, which is, you take an element y and you send it to u of y, and you take an element z and you send it to v of z, that statement is just saying that map as a function is continuous. Right? The topology of the disjoint union is set up precisely so that that works. Okay, so we've got this continuous map. Let's call it sort of reuse matrix notation. So that's just a name for this function. Well, and observe that if I feed into that function a pair of things which are in the equivalence relation. So let's say f of x. Right, so what's going into this function as an element of the disjoint union? Suppose it's something of the form f of x. That is, I applied f and then I thought about the image as an element of the disjoint union. Well, that's a y, right? So the output is using the first component. So that's u of f of x. But by commutativity of that diagram, that's v of g of x, which is what I would get if I applied this new map out of the disjoint union to g of x. Right, so I've got a continuous map which at least sends the generating pairs of my equivalence relation to the same element of W. But as we just discussed, the set of all pairs which are going to the same element is an equivalence relation. So if it contains the generating pairs, right, that was what this discussion was about. So if it contains the generating pairs, then it must contain the equivalence, the entire equivalence relation. So therefore, if, I don't know, Q1 is equivalent to Q2 in the disjoint union, no matter what elements they are, then UV Q1 is equal to UV Q2. Of course, it's not a big chore to think about what the actual equivalence relation generated by those pairs is, but I'm doing it in this way for a very deliberate reason, which is because later we won't want to have to think that through. So I don't want to have to do it even in this case. Okay, so the function u comma v sends everything in the equivalence relation to the same equivalence class, and therefore by this property of the quotient, right, so I'm writing the bar there. So you could write little f bar for that map out of the quotient, right? That would be a typical thing to do. Okay, so this map induces a unique continuous map out of the quotient, which makes the analog of that diagram commute, and that's what we call T. That's doing, if you think about it, exactly this, which is what it had to do. So it's unique in particular. Okay, so we constructed a continuous map which made those two triangles commute, and because of the argument at the beginning, it had to be unique. So that's it. All right, and that was using the properties of the disjoint union and the quotient. Okay. So if you're following the notes, I'm going to skip to page 12 and come back to some of that material. So I want to give an example of this quickly. All right, so what's an example of this pushout? I said it was about gluing, and here's why. So let's take a graph. So what's a graph? Well, I mean a finite unoriented graph, so it's just a finite set of vertices and a finite set of unordered pairs of vertices. Okay, maybe empty. All right, so that's my graph. Now a graph clearly sort of has some topological content as soon as I draw it on the board, right? Yeah, I mean, I allow multiple edges as well, so E is not actually a set. Yeah, let's say it's an indexed family of unordered pairs of vertices, okay? Right, so there's an example of a graph with 4 vertices. Well, if I told you to think about that as a space, you'd have no problem doing it, right? You just think about 1, 2, 3, 4, 5, 6 intervals sort of glued together in some way. All right, so let's realize that process. I mean, this is the simplest case of constructing what's called a CW complex. So let's realize this process is starting with a discrete space, which is the set of vertices, and attaching the edges in the process using this lemma. So okay, so by a discrete space, I mean every set is open. Okay? So I take the set of vertices and I take the topology, which is all sets are open. So I'm going to glue in the edges into that space. So I need to define n cells and their boundary. So S0, I mean sort of the zero circle, which is a pair of points. Right, so get some definitions first. So Sn, the n sphere, is all those points in Rn plus 1 whose usual Euclidean length is equal to 1. Right, so S1 we've discussed, S2 is the sphere, and so on. The superscript here means the dimension, so to speak, of the space. We haven't defined dimensions of topological spaces, but take the intuitive notion you have of dimension, and that's what the integer here is telling you. Similarly for the disk. Okay, so the n disk is again n-dimensional and sits inside Rn. So So the n-1 sphere sits inside the n disk. Just by inclusion from the definition. So for instance, S0 sitting inside D1. Well, what's D1? That's all the points in R1 whose norm is less than or equal to 1. So that's just the interval between -1 and 1. And S1 is, well, just the points -1 and 1. And then this map is just the map which sits the endpoints of the interval inside the interval itself. And similarly, so if I take the usual circle in the plane and then the disk in the plane, then the circle sits as the boundary of the disk. Okay, so the former case is what I want to think about now. So, well, clearly those are vertices and edges, right? So for each edge in my graph, say E, let F sub E be the map from S0, what's S0? It's a pair of points with the subspace topology in Rn+1, so it's discrete, right? To tell you a continuous map out of a discrete space, I just need to tell you a function because every subset is open. So to tell you a continuous map from S0 to X0, I just need to tell you a pair of points of X0. And there they are. You send -1 to V1, the first point on the edge, the vertex on the edge, and 1 to V2, the second vertex on the edge. That seems non-symmetric. Actually, it turns out to be symmetric in the end. All right, but anyway, choose an ordering for the moment. So we get a continuous map for every edge. Right? Well, that's a family of maps, or the same domain and codomain, but just pay attention to the fact that the codomain is always the same. By the definition of the disjoint union, if I have a bunch of maps out of a family of spaces into the same space, well, take the disjoint union over the edges of copies of S0, this pair of points. So let me maybe label the copy of S0 corresponding to the index E with a subscript bracket E. And then if I restrict, so this is the unique map induced out of the disjoint union. It's unique such it's continuous, and when I restrict it to the copy of S0 corresponding to E, what I get is the map FE. So that's a continuous map. But now I also have a family of continuous maps out of that disjoint union of the S0s, which is I just take one copy of the disk. Okay, so again, D1 sub E is just D1, which is the one disk, which is just an interval. And I take the disjoint union over all the inclusions. So that is to say, this just takes a point which sits in the part of this disjoint union which is indexed by E and sends it to the same point, well, if you like, iota of X. Right? It just sits that point in that copy of S0 inside the corresponding copy of D1. Okay, so definition, the topological space associated to the graph is the pushout of those two maps I've just written down. Well, to form the pushout, I just needed two continuous maps. What's the pushout? It's the thing that's going to take the disjoint union of those two vertices. So it's going to take the disjoint union of all the vertices with, well, already a disjoint union of a bunch of lines. So I've got vertices over here, then just a bunch of lines, one per edge, and then it's going to glue them all together. That's what the equivalence relation does. It's going to glue them all together such that that's the minimal way of gluing, which makes those two paths out of the set of sort of doubled up vertices commute. So by this I mean, so it's this. Okay, this notation's gross. I'm not going to write it. So this is the push out of those two maps. Those are the F and G. Okay, so I claim that is this picture. Right, to think about why, I think you just have to pay attention to what the generating equivalence classes are. So to form this, I'm taking the disjoint union I just said, modding out by the equivalence relation, which says that for everything in here, so for every x I get one equivalence relation. But all the x's in here, I mean, it's a disjoint union, so I can really pick an e and then pick an x. So for every e in E, and for every x in S0E, so that just means either plus or minus 1, right? So this is the x corresponding to the E. I have to make f of that agree with the thing down here. Well, f of that is V0 and V1, right? Or V1 and V2, whatever. So corresponding to, so if I took minus 1, I'd get this. And then if I took minus 1 in the copy corresponding to E here, what I'd get is the end, one end of the interval, right? So here's my interval corresponding to E. I'd first, the minus 1 case would tell me I need to glue this onto that. Maybe it's better not to draw it with the same color as edges. So green lines mean identify. Right? So here's my collection of vertices in my disjoint union. Here's my collection of edges. The gluing says glue that guy to that guy. That's what the minus 1 corresponding to E says. The plus 1 corresponding to E says glue that guy to that guy. And then, well, every time I've got another edge, say I have two edges which go between the same vertices, well, that'll be glued to that, and that'll be glued to that at some later point, right? So that, and that will all be the same point in my topological space. So I took all the edges and all the vertices separately, then I connected vertices to the ends of the intervals, and in that way I crush everything down until it looks like the space itself. Okay, so that's it for attaching one cells or one disks to 0 cells, that is vertices. We can do this more generally to construct CW complexes. Those are the prime examples of compact Hausdorff spaces. So, all right, I'll stop there for today.